Hello, I'm Clive. The purpose of this video is to introduce a playlist on mathematical proof, and first of all to recommend some key books that I've used to understand and deepen my understanding of what a mathematical proof is and how to practice and apply those techniques to a range of different mathematical questions. I'm English, you may have guessed, so I will use the word maths rather than math in my video. Hopefully that won't cause too much of a problem. Now, proof is a topic that's really the bedrock of all mathematics beyond making calculations. At university level and beyond, it's possible to say that maths is all about the application of proof to any mathematical topic. In proof, we try and address the most general ideas and objects rather than particular values. A proof will be about integers or positive real numbers or irrational numbers or matrices, but not about calculating the roots of a quadratic or polynomial equation. First of all, I'm going to give you some definitions of words that I'm going to use in the video, and I've checked these and hopefully they're going to be consistent with other people's use of these words in proof. So a statement is a collection of words that is either true or false, and it must be one of them but not both. So I am wearing blue shoes is either true or false. I have 15 fingers on my left hand is either true or false. Miami is the capital of Costa Rica is either true or false. Are you going to Edinburgh is itself not a statement, it's a question. Whereas I am going to Edinburgh tomorrow is a statement. It's either true or false. A proposition is a statement that is definitely true or false. For example, 5 is greater than 3, or 3 is less than 5, or 3 is greater than 5 are all propositions, either true or false. And in the definitions that I've seen, a proposition is sort of innately or just is true. Now we start getting on to proof-specific words and definitions. A conjecture is a statement that we don't know is true. We might believe it's true by having tried and applied certain numbers, but we're being challenged to show that it is true. So a theorem is a proposition that requires some kind of logical argument, a proof, to establish it is true. For example, there is no largest integer, or two odd numbers added make an even number. Both are true, but require relatively simple proofs to demonstrate that they are true. So they're theorems. Before it was proved, Fermat's last theorem was actually Theorem's last conjecture. It only became a theorem when it was proved by Andrew Wiles in the mid-1990s. But people are a bit loose about their use of the word theorem, proposition, conjecture, except in mathematical terms. Now, for the simple proofs we're considering, they will all be of the following form. We accept that something's true, let's call it P, and we're being challenged to demonstrate or prove that something else, Q, is true, only using P is true, and using the laws of logic or maths, or both, usually both. What we're working from, P, can be called the hypothesis, or the premise, or the antecedent. What we're working towards, what we're trying to prove is true, Q, is the conclusion, or the result, or the consequent. I may use any one of those words in the following videos. Hopefully I'll use the words correctly and consistently in this and the following videos, especially as these are videos about proof and mathematical truth. Now I'm going to introduce some of the books that I've used to expand and deepen my understanding of proof. First of all, a relatively slim book Keith Devlin's Introduction to Mathematical Thinking. Now, one of the features of it is it's a small book, and it's a good place to start. It doesn't overburden the reader with technical details, but it is thorough. Now, it starts off with not specifically mathematical examples, but ones that you may be more familiar and make more sense relating to real world situations. Then Keith Devlin introduces mathematical notation, such as what do we mean by a mathematical statement, and the logical connectives, such as and or, and how to combine them together. For me, what really appealed about this book is the section in chapter 2, section 2.3, about implication or if-then statements. And a real revelation to me is something that had never been pointed out before. You may be able to see it here. And that implication is the conditional plus causation. Now that's explained more deeply in the book, but basically when we use the word implies, either in language or in maths, it often contains the idea that what we're working from, the antecedent, causes the result or the consequent. Whereas Devlin says in mathematics we've got something that's a little bit more sparse, a little bit more precise, and that's the conditional, and that we can use logic based on the conditional, and we don't have to strictly say that the antecedent causes the consequent. Okay, that may be a bit esoteric, but it helps understand why the truth table for the conditional is the way it is. And then he goes on to building more complicated truth tables and uses those to underpin why certain proof strategies are the way they are. Then he includes a topic that is common to all proof books about quantifiers, and then a bit on proof by induction, and finally the real numbers. So this, although it's small, very good place to start. Good book. Okay. The next book, which is my current favorite, is How to Read and Do Proofs by Daniel Solow. Okay. Now this is backed up by some videos that you should be able to find on YouTube. I've got the 5th edition, and the videos I think support the 6th edition, but they can be mapped over quite easily. The coverage is the same as other books, such as the different strategies and methods such as contradiction and contrapositive, but he has in here, for me, a very useful, or two very useful ideas. One is what's called the backward and forward method or process, and you've got this diagram here. So this is where we're starting. This is our haystack. This is what we're trying to prove. Well, this is where we start. This is what we know or assume to be true, and we're trying to get here. This is our conclusion. Okay. And one way of thinking is we start here and we go through our haystack and we end up here at our result. But in fact, the method that Solow uses, which is very powerful and can be applied in lots of circumstances, you actually start at the end and you say, essentially, what would need to be true here so that the result we ultimately want must also be true. And part of that is creating what he calls the key question, which is cast in very general terms, not using specific values or letters from the question, but something like, what do we get when we add two irrational numbers, for example? And then that becomes our new goal, and you keep on working backwards until you either get stuck or you arrive at what you have assumed to be true. If you get stuck somewhere here, and the details and the examples are in the book, what you then do is use the forward method to say, given what we're given, what can we deduce? And you can deduce lots of things, and what you're trying to do is make those two meet up in the middle. So the idea of the backward forward process or method, and the key question is really the powerful idea. And as always, lots of very graded examples which reinforce the ideas and approaches that he's got in the book. Then he goes on to address quantifiers, then essentially for all and for any, and there exists one. Then he tackles how to apply what you have used to the contradiction method. And again, another idea in here is that when you have a contradiction proof, if something is true, then something else is not true. It's this idea of how do you get started? And basically, it's most easily understood when we have if something is true, proving something else is not true, okay? And or in symbol terms, if P, then not Q. And the essential starting point is one, to recognize that, and two, to recast that in terms of assume P and Q are both true. And from that, you deduce the contradiction, and via logic, which he explains, that must mean the original conclusion that Q is not true or Q is false must be true. Sounds a bit convoluted, but it's that first step of changing if P then not Q into assume P and Q are both true, then deriving the contradiction gets you started with proof by contradiction. Very useful way and clarification of how to tackle those kind of questions. The next one, this used to be my favorite before Solow, but this is still very, very good, and it covers the usual ground. This is How to Prove It by Daniel Velleman. A bit thicker, lots of examples, and it covers all the standard material, but it has some other stuff which I think is very useful, but is a little bit more challenging than the material in the other book. Not that Solow isn't thorough, but there's material on proof strategies here, which is also in Solow, but I like the way that Velleman tackles it, and that's chapter 3, okay? And basically, what he does is he takes each type of proposition or conjecture that you're trying to prove, and he analyzes the structure of it. So, for example, he divides what you have in the conjecture into givens and the goal. Okay, so here's an example. To prove a goal of the form not P. Okay, so this is what I talked about before. What Velleman does is says if you're trying to prove something is false or not true, so for example, you're trying to prove that a number is irrational, what you do is you assume the opposite of that. You assume that a number is rational, and the strategy is to end up with a contradiction. Okay, and if you're given something of the form not P, then your goal is a contradiction, and the contradiction might be is you end up proving that P is true. So you're given that P is false or not true, so P is an irrational number, and if you can by your proof prove that a number is rational, then you have a contradiction. And especially he has quite a few examples on how to prove things with sets, particularly using quantifiers. Section 2.3 is on sets, but I think you should come back to that after you've read another book. Okay, I'll come back to that in a minute. The next book is quite a big book, okay, and this is really good, very clear, is Proofs by J. Cummings. So any of these books would be really good, and I just like them for different things, although maybe Solow with a very close second place, Velleman, or J. Cummings would do the whole job to get you started and quite a way forward. Now, again, same kind of content, okay, but what he does is tackle particular topics like divisibility and modular arithmetics, and his layout is very much, you come up with a proposition and then he says, well, let's try and see whether it seems to be true by trying some examples, and then trying to use that approach in the specific examples to generalize it. So again, he has a different way of presenting it, but how to use the conjecture and sort of take it apart as a way to structure how to tackle the conjecture you're trying to prove. Also, at the end of each chapter, it has sort of a little extension bits that show you what else you can do with the material he's just covered. So, for example, Introduction to Number Theory. Again, Cummings has a chapter on sets. He uses diagrams, kind of conventional, familiar diagrams, a bit more to underpin and justify and illustrate the conjectures, or in this case, theorem of De Morgan's law with sets, and then how to prove it using particular set operations. Now, in order to do the set questions, and sets are really useful and they're very powerful and basically underpin a lot of modern mathematics, okay, what we have to do is understand set theory, okay, and there's this slim book, and this is Naive Set Theory by Paul Halmos. It isn't strictly a book on proof, but it starts off with some unfamiliar material to give a rigorous basis for what we mean by sets, the axiom of extension and the axiom of specification. Okay, now that may seem a bit dry, but the key idea that comes across quite early in Halmos's book is that for two sets to be the same, then you take one of two approaches. You prove, if you've got two sets A and B, then A is a subset of B and B is a subset of A, is one technique. But the other idea that is used to prove that is if we take an arbitrary element of A and we show that it must necessarily be also in B, and then if we take an arbitrary element of B and we show that it must also be in A, that results in every element of A is in B and every element of B is in A. So they're actually equal to each other. And then, having understood that and how to do questions of that style, I would then go back to the set examples and questions in Halmos, in Velleman, and also in Cummings. Okay. Separate from that are two other books which are available online to download and are free. The first one is The Book of Proof by Richard Hammack. Okay, and here if we look at the contents, Hammack starts off with sets and their definitions, and then he talks about the basics of logic, the elements of it, the what a statement is, the connectives and, or, and not, and quantifiers, and then goes on to techniques of proof. Again, what do we mean by direct proof? How do we apply it? The contrapositive proof, proof by contradiction. Okay, and then in chapter 8, he's got proving conjectures about sets. Okay, and then quite a nice example, quite a nice topic is disproof. How do we determine that what is put forward as a proof actually isn't a proof? okay, and then mathematical induction, and then some other topics which are in other books, such as functions. Another very thorough book that's available for download for free online is Introduction to Proofs and the Mathematical Vernacular by Martin Day. Okay, and he starts off with some example, launches straight into it and says, well, here's what a proof looks like. Okay, and then goes into, as some of the other books, as to what are the key elements of proof, such as what do we mean by a statement, what do we mean by and, or, and not, and how do we combine those to make more complicated statements. Okay, then goes into quantifiers, and finally into implication or the conditional. Then sets, and chapter 4 about what do we mean by integers, what do conjectures and proofs and theorems of integers look like, and then ends up with linear algebra. And a very popular kind of question is about number theory, which is to do with the properties and behavior of integers. So hopefully that's given you a flavor of some of these books. I wouldn't say that any one is better than the other, and they cover different areas, but there are particular things in each of them which for me really clarified particular ideas or approaches within proof, and I continue to use all of them and then go back, and as always when I read a chapter after having read a different book, I'll get more out of it on subsequent reading. So hopefully you find that one of these books is useful to you, and I'll be drawing on them, not copying the content, but using the ideas in my other videos to focus on particular topics in proof, starting with what do we mean by a statement? What do the connectives do? How do they affect the truth of a statement? Then particularly, how do we understand and use the conditional or implication? Then taking particular examples of conjectures, analyzing their structure, and devising a strategy, either using ideas from Velleman, Solow, or from Velleman or Solow in particular, as to how to tackle a particular, identifying what the information in the conjecture is, and how to then go about starting the attempted proof and how to proceed with it. And hopefully you'll find this video, the subsequent videos, and the apps useful to get you started on doing mathematical proof. And as always within maths, the important thing is just to practice. Don't start too complicated. Start with things that are quite straightforward. Make sure you have a fairly good grip of why things are the way they are. You don't have to be 100% on top of it, and then proceed to more challenging questions. Okay, speak to you soon. Bye.